All right, so we got to talk about now solar energy and how it gets transferred on Earth. Okay, so this is kind of part of the idea that we're trying to incorporate several of the units together. A little bit of biology, a little bit of chemistry, and a little bit of physics, kind of energy with life and stuff. Yeah, okay, that's what we're trying to essentially do here. So we're going to look at what happens when solar energy strikes the Earth. All right, obviously solar energy is very important. It is the only source of energy on Earth. Okay, every other form of energy, okay, essentially comes from the sun, with the exception of maybe gravitational potential. Okay, but okay, all the other forms of energy, originally at least, came from the sun. So if an environmentalist ever gives you a hard time about driving a big V8 vehicle, you can tell them it's okay that it's solar powered, because it's not a lie. Okay? The fossil fuels you're burning used to be plants. And they captured the sunlight and made it into sugars, which then over 500 million years or so were turned into fossil fuels like oil and coal. So you're all solar, where everything we do is solar powered, at least indirectly. That won't make them feel better, but it might make them quiet. Something to think about. Okay? I tried it once and they really didn't like the answer, but it's all right. Okay. All right. So we're going to look at the three parts of the Earth. And when I say the three parts of the Earth, I mean the atmosphere, the lithosphere, which is the solid or rocky part of the Earth, okay, and the hydrosphere, which is all the water. All right, so we're going to be looking at those three things because they all interact with solar energy a little bit differently, and they all have a role to play in transferring that solar energy. Because we looked at the other day, when we looked at the effect of latitude on climate, okay, we saw that at the equator, energy is more direct. Solar energy is more direct. More energy is captured at the equator than at the poles. So there's got to be a way to transfer that energy away, because naturally heat flows from hot to cold. So the second law of thermodynamics has a lot to do with why the equator is not boiling hot and the poles are not frozen cold. I mean, yeah, they are cold, but they're not, there's not a huge difference there. If the Earth didn't do kind of some of the things it does, there'd be a scorched line at the equator and there'd be absolutely nothing at the poles, and there'd be this two temperate areas in between. Okay, so it's very important that energy is transferred, okay, from one place to another. All right, so we're going to look at also how energy on Earth is absorbed, used, and reflected. These three words are important, okay, because these are the three fates of solar energy. Okay, when solar energy strikes the Earth, one or more of those three things is going to happen. All right, some of it will be absorbed, some of it will be reflected, and some of it will be used. There is only one process on Earth that natural process. That's the key here. We are talking about only natural processes that can convert solar energy into chemical energy, and that is photosynthesis. Okay, so, okay. If something's being used, that's photosynthesis. Okay, and it is important for you to realize that we are only talking about the natural processes. Okay, because oftentimes I'll ask a question on the unit exam, and I'll say, solar energy strikes a section of, prairie near Okotoks. What could happen to it? And inevitably I get, it probably hit solar panels and was converted to electricity, and then I go, okay, the last time I checked, the section of prairie out there does not have solar panels all over it. Okay? Don't write solar panels. Don't write solar panels. Okay? We're talking about natural processes. If it hits a section of prairie, okay, it's hitting plants. All right? Unless it's hitting it right now, in which case it's hitting snow. I hit myself a lot harder than I'd anticipated there. Okay. So yeah, it's hitting snow. Well, if it hits snow, what's a lot of it doing? It's getting reflected, because snow is highly reflective. It's white. White reflects all colors of light. Okay, so some of that influences how much of the energy is getting used. Okay, or how much of it is getting absorbed. Okay, in the summertime, a lot more energy gets absorbed. Agreed? Right. Without snow there, the land's not as reflective, so it absorbs more of the energy and it gets warmer. Okay, we use this idea, right? And in fact, we are using it right now. It's been fairly nice the last couple of days. What have you noticed about the roads? Yeah, they're getting clearer, because what did we put all over them? Well, a little bit of salt, but also with the salt we put gravel and sand. Yeah, why do we throw the sand on there? Okay, well, a little bit for traction, but you probably noticed it doesn't really stay in the places where people's wheels are. It always gets kind of pushed to the sides. The main purpose of sand on the roads, okay, is also to increase the amount of solar energy that gets absorbed. It's darker. Okay? Darker colors absorb more stuff. You ever notice how, like, if you have a black interior in a car versus a light interior, it's always hotter? Okay, black absorbs more energy. Okay, darker colors absorb more energy. We throw sand on the roads. Okay, they're going to absorb more solar energy and they're going to melt faster. Okay, everyone kind of follow on that. And you probably noticed that there are some roads that clear before others, like going down 32nd here. That road clears faster than any other road in town. Okay, because it faces south. Okay, especially the hilly part going down to the dog stadium there. Okay, faces south. The sun shines on it all day. Okay, whereas if you're going on the the other end of town, going down a hill that faces north, okay, it's not going to clear nearly as fast because the sun's never shining on it. Okay, so absorption of sunlight is an important way to get temperatures to go up. All right, so used is photosynthesis. Absorbed means there's going to be an increase in temperature. Okay, reflected means no change. If it just bounces off, okay, then essentially nothing happened. All right, questions there so far? Okay, so those three terms, if I ask you what happens to light when it strikes the earth, absorbed, used, and reflected, and then talk about when it's absorbed, temperatures go up. When it's used, it's photosynthesis. When it's reflected, there's no change, right? It just bounces off. Okay, so let's talk about the atmosphere first. The atmosphere is the most important part of the Earth when it comes to energy transfers. Okay, the reason being, it's fluid. It's the most fluid of the three parts. Okay, yes, the hydrosphere is also fluid, but the ocean isn't in contact with the entire Earth. Okay, it's trapped in the low places, whereas the atmosphere is a blanket that covers the entire Earth and is, because it's a gas, more fluid than water. Okay, so it very easily moves and transfers energy. What do we call it when the atmosphere moves and transfers energy? Okay, I was not thinking of a specific kind of this. Wind, yeah. Okay, wind happens because energy is being transferred. There's a difference. There's high and low. Okay, and energy is trying to move. Okay, to do that, it's got to take the wind. It's got to take the air with it. That's wind. All right, so the innermost layer, and I'm never going to ask you about the layers, okay, but the atmosphere is layered. You're not going to need to know the layers, okay? The troposphere is probably the most important layer. That's where most of the stuff goes on, okay? That's where we live, it's where the atmosphere is thickest. It's thickest because gravity pulls all the heavy gases down, okay? So nitrogen and oxygen and carbon dioxide all kind of stay in here, okay? The stratosphere is kind of important, okay, in that there's a few very important weather mechanisms that run in the stratosphere, namely the jet stream. How many people have heard that term before? Okay, and we'll talk about the jet stream more tomorrow, but okay, it's an important wind pattern that occurs in the stratosphere. Okay, and then above that, the atmosphere is pretty thin. You're essentially in space already. Okay, basically you get to the mesosphere is kind of just a transition between true atmosphere and space. The thermosphere and exosphere are essentially space. It's where the magnetic field and Van Allen belts and stuff would be. Okay, it's where the auroras and stuff would happen. Okay, so how many people have seen the northern lights before? They're actually, unless they're really bright, they're hard to see from Okotoks because you got to look through Calgary to see them, right? And Calgary's got a lot of light pollution. Okay. All right. Ozone gas is present in the stratosphere. That's where the ozone layer is. Okay, and the ozone layer is making a comeback lately. Okay, back in the 70s and 80s, it was in really bad shape because we were using a lot of chemicals that broke down ozone. Okay, ozone breaks down naturally on its own, but it also reforms. But we were using chlorinated fluorocarbons, CFCs, okay, that were really bad for the ozone layer, and it was destroying. There was a big hole in it over Australia. Incidentally, Australia has the highest rate of skin cancer of any country on Earth. Possibly the two things are related. Okay, the Australians love to be on the beach. They're very outdoorsy people. So okay, there's also a hole in the ozone layer, and they like to be outside. Really bad combination of things. Okay, but yeah, there was a big hole in it, but it is starting to shrink because we've eliminated CFCs from the things we used them. And they used to be the propellant in aerosol, all aerosol cans. They used to be used for refrigerants and refrigerators, okay, stuff like that. We've eliminated all of that now, so we're not putting off as many of those. All right, so the atmosphere plays this critical role in maintaining the Earth's temperature. It's essentially a big insulator, okay, that keeps energy from escaping into space. Does some energy escape into space? Of course. If it didn't, if it all got trapped, Earth would not be the very nice place that it is. It would be more like what? It would be more like Venus. Okay, Venus has a very thick atmosphere. Okay, about 100 times thicker than Earth's. It's all carbon dioxide, and it's got this massive greenhouse effect as a result. And so it's hot enough to melt lead on the surface. Okay, it's hotter than the inside of your oven. Okay, on the surface of Venus all the time because it's got this massive runaway greenhouse effect. On the other end of that, our other neighbor, Mars, has an incredibly thin atmosphere. It's almost 100 times less dense than Earth's, and everything just escapes, which makes it quite a bit colder. Right? Yes, it's further away as well, but okay, those distances actually don't make as much difference as the thickness of the atmospheres do. Okay, so the atmosphere is pretty important in trapping some of that heat and harnessing it, and of course allowing it to transfer. Okay, so when we've got incoming solar radiation, okay, a lot of it gets backscattered. Okay, that means certain wavelengths of light, when they strike the Earth's atmosphere, just bounce all over the place. Which wavelength in particular? Blue. That's why the sky is blue. Okay, the sky is blue because blue light scatters when it strikes the gases in our atmosphere. Okay, it isn't because it reflects off the ocean. I think we had that talk before. Okay, it's scattered by the atmosphere. All right, so that stuff never actually gets to the surface. Okay, and other wavelengths of light that come from the sun are also usually reflected or blocked or scattered, which is good because a lot of them are bad. Okay, like gamma rays and X-rays and UV, okay, those are all bad for us. Okay, luckily the Earth's atmosphere and magnetic field and stuff protects us from most of those. Okay, yes, the UV light can get through, but a lot of it gets scattered as well. All right, so we got incoming solar radiation. Some of it gets reflected by clouds. Okay, some of it hits the Earth's surface and bounces off. Okay, some of it gets absorbed. Okay, when it gets absorbed, then the temperature of the Earth will go up, and the temperature of the surrounding air will go up. Okay, some of it is absorbed by water vapor and gases. That'll increase the temperature of the atmosphere. Okay, and then some of it just is radiated away. Okay, there's heat sources on the Earth, and when there's heat sources on the Earth, they radiate heat into the atmosphere and even out into space. Okay, so yeah, that's some of the stuff that can go on. Now, difference between summer and winter. Okay, in case it wasn't obvious enough that this is summer and this is winter, I'll label it. Okay, the amount of energy that gets absorbed is a lot different. Okay, and of course we talked about the other day how the seasons also affect the quality of the sunlight that comes in. Okay, so we've got in winter, okay, we've got low angle, low intensity sunlight coming in, and when it hits the surface of the Earth is, well, right now covered by snow. Okay, 85 to 90% of the light reflects off the snow. Okay, so very little of that poor angle solar radiation is being kept. Okay, only a very small percent, 10 to 15%, actually gets absorbed. Now, that changes as the type of snow changes. Okay, right now, more of it would be absorbed because the snow is compacting because it started to melt. Dust has landed on top of it, which increases its absorption. Okay, things like that. But if it's fresh, like powdery snow, then a lot of it reflects off because it's very pristine, very white. That sort of makes sense? Okay, so in this situation, we have what's called a high albedo. Okay, that's a term you'll need to know. High albedo means highly reflective. Low albedo means very absorptive. Okay, so in the summertime, we have a very different situation. Okay, plants are growing, so they're absorbing a lot of sunlight. Okay, soil and things like that are exposed. They're darker in color, so they have a low albedo. We're looking at 70% absorption. Okay, 20% reflection, 10% reflection off liquid water. Okay, you'll notice there's no difference here between reflection off the soil and reflection off the water in the winter because they're frozen, right? So it doesn't really matter. It's covered in snow anyway. Because the Earth is tilted. Okay, so we've got the Earth's tilt like this, right? So let's say the sun is over here. The sun's over here. They're not that close. Okay. The Earth's tilted 23.5 degrees. Okay. On the winter solstice, we're actually 23.5 degrees tilted directly away from the sun, right? So the sun's light hits this side of the Earth. So when the Earth is spinning on its axis, it's spinning like this, right, on its axis, weirdly. Okay, so as it's doing that, if we're located, let's say here, we spend more time in the dark than we do in the light. So we have shorter days, but we also have less direct sunlight. If I'm at the equator, the sunlight is right overhead, beating down on me. Here, that same amount of sunlight is less direct because I'm further away and angled to it. Okay, so it's less intense and less concentrated. With me there? Summertime, the opposite occurs. Okay, in the summertime, June 21st, okay, we're tilted directly towards the sun. Well, now that sunlight is much more direct because we're actually down here now, right? Not that far. I'm exaggerating it quite a bit there, but okay, we're in more direct sunlight, and when the Earth rotates, we're in the sun more, right? Days are longer. Right. And so in Australia and New Zealand, it's wintertime. Yeah. Does that make sense? Okay. All right. So albedo, important term. Got to know that. Okay. Because it has to do with absorption, reflection, and use. Okay. Goes together. So when you're explaining those three things, albedo should probably be part of that explanation. All right. Now, in the atmosphere, obviously, there's gases in certain concentrations that are important. Okay. We want to have, obviously, oxygen. Okay. But how much of the Earth's atmosphere is actually oxygen? Yeah, about 20 actually, maybe a little less than 20. Okay. Well, actually, sorry. Yeah, it's a little more than 20. But most of the Earth's atmosphere is actually nitrogen. It's actually this N2. That's the most common gas in the Earth's atmosphere. Very high percentage of it. It doesn't affect us in any way. We breathe it in, we breathe it out. We don't use it for anything. Okay, it doesn't really convert to anything in our body. It's just always there, right? But it does contribute to atmospheric pressure, and atmospheric pressure is important. Okay, we have to have a certain amount of that. If we don't, okay, it really changes how our body works. Okay, this is something that mountain climbers deal with. Okay, if they ascend really quickly or get to the point where they're in what's called the death zone. Has anyone ever heard that term? Okay, when you're climbing Everest, you get above a certain point, you're in the death zone. Okay, it's because the atmospheric pressure is so low that the fluids that are normally retained in your blood start coming out. Okay, and other gases also start to bubble a little bit. Okay, it's called you can get dysbarism, which is the bends. Okay, has anyone ever heard of the bends? You don't really get that climbing mountains. You get it more if you come up from scuba diving too quickly. Okay, if you scuba dive, you go down really, really deep. The pressure on you is far greater, so more gases can dissolve into your blood. Okay, if you come up too fast, they can't stay in your blood. It becomes like saturated, so they bubble instead of precipitate. And if you get bubbles in your blood, that's bad. They're very painful. Okay, because those bubbles will get lodged in the small blood vessels, and then it is like extremely painful and very dangerous. If you get those bubbles lodged in the small blood vessels of your brain, they can rupture, and then you have like an aneurysm, okay, a brain bleed, okay, and that can kill you. So if people get the bends, they have to put them in an iron lung, okay, which is like this big hyperbaric chamber, and put them under pressure to get that stuff back in, and then slowly release the pressure. Okay, several days they'd spend in this metal box. Okay. If you're climbing a mountain, it's more about fluids. There's not enough pressure, and so you start to actually drown in your own fluids because they'll come out into your lungs. Okay, and you get like this really bad cough that you can't get rid of. Okay, it's called pulmonary edema. Okay, you essentially just drown. Okay, even though you're not in water. Right? Yeah, it's pretty bad, and they have to watch for that. They carry climbers who climb Everest will carry multiple syringes of what they call Dex. It's the stuff that's in cough suppressant, dextromethorphan. Okay, if you ever read what's in like NyQuil, it's one of the ingredients in there. It's a cough suppressant. They'll take needles of it, several of them, and they'll inject themselves when they start to get that, okay, in order to keep from coughing, because they'll cough so bad that they'll rupture blood vessels in their throat and blood will rush into their lungs. Okay. I don't know why people do it. I get it's exciting, but it's also a lot of people die. Yeah. So yeah, atmospheric pressure, very important. That's what you're supposed to get out of this. Kind of got off track there. Okay, so all these other gases are also present. Carbon dioxide is important. Make no mistake. If there was not carbon dioxide in the atmosphere, Earth would be a very cold place. Okay, we need a certain amount of carbon dioxide. We need a small, effective greenhouse effect. Without it, Earth would be too cold. Okay, now I'm not saying that means, hey, idle your car for 2 hours before you get in. That's not smart either. Okay, but certainly we do need some carbon dioxide, okay, in the atmosphere because it's important. It's also the food source for plants. Yeah, without carbon dioxide, there's no photosynthesis. Okay, that's the food source for plants. So there's got to be some of that in there. Okay. Oh, I put this picture on here because it I was talking about the rain shadow effect the other day. Okay. This is Mount Robson, and oftentimes, even on a clear day, the top of Mount Robson will be shrouded in cloud because it's so tall. Okay, like if a warm air mass just approaches the mountain, it can't go past it, so it goes up and over. And as it goes up and over, all the moisture in it condenses and falls as snow on the top of the mountain. But you'll just see it'll be bright and clear, and then all of a sudden this cloud will appear out of nowhere. Okay, that's kind of that rain shadow effect. The moisture gets pushed up high enough that it falls out on the mountains and then comes down the other side. So just remembered I had a picture of that. So okay, the hydrosphere. Okay, so all the water on Earth is considered to be the hydrosphere. Okay, that's water in the ocean, water in lakes, water in rivers, water underground. Okay, that would be trapped in aquifers and wells and things like that. All the water on Earth is part of the hydrosphere. Now, water that's trapped underground doesn't really have much to do with energy transfers. Okay, obviously it can't because it's trapped underground. But water on the surface does play a big part in that because of something called latent heat. And we'll talk a little bit more about that later, but latent heat is the energy that water vapor carries with it as a result of having turned from liquid water into vapor, okay? Because that takes energy, right? So that the water vapor will carry that with it, and then when it condenses, that energy will be released. Okay, so sometimes a lot of energy can be carried from the equator to more northerly areas in the form of water vapor. Okay, and then when it condenses, it will release it also. That's a big part of the role of the hydrosphere. Okay, the other role of the hydrosphere is that it's a heat sink. Okay, and we talked about how being close to the ocean can sometimes make your climate more mild because the ocean can retain a lot of energy. Okay, so that's another role in terms of energy of the hydrosphere. Okay. Now, this is another important, not that I'm ever going to ask you about this number, but less than 0.1% of all the water evaporated from the surface of the Earth is returned to lakes, streams, or seeps into underground hollows. The rest runs off, eventually ends up in river systems, and goes to the ocean. Okay, so when you think about how much water evaporates from here, okay, all the time, every day, does it rain here every day? So then what happened to all the water that evaporated here? Yeah, it goes somewhere else. It gets blown somewhere else. Okay, and then also, we get a thunderstorm or we get, a huge amount of hail, whenever. Well, we got a whole bunch of water that definitely didn't come from here. Okay, it evaporated from somewhere else and it comes back. So understand that the water cycle isn't, okay, the water evaporated here, it's got to fall right back here. It doesn't work. It's not that perfect. Okay, in general, does it, kind of get everywhere on average? Yes. Okay, but there are places on Earth where there's more evaporation than there is precipitation, and there's areas where there's more precipitation than there is evaporation. Okay, those areas tend to be wetter and the other areas tend to be drier. All right, the water cycle. I know you've been beat over the head with this your whole life, but one more time. Okay, we got to talk about the parts of the water cycle in terms of energy. Okay, so water cycle starts with either one of these two processes, either evaporation, so that's just liquid water turning into water vapor, or transpiration. Sometimes it's called evapotranspiration, but we usually just call it transpiration. That's water vapor that is evaporating from plants as they carry out photosynthesis. So transpiration means it's coming from plants. Evaporation means it's just water turning into water vapor. All right. So those two processes get water vapor into the air. With that water vapor comes latent heat, a bunch of energy. Okay, then that water vapor will move over, it'll begin to cool, and it will condense. When it condenses, okay, it releases all of the latent heat, so it's a way to transfer energy. Okay, when it condenses, it falls as precipitation, hail, rain, snow, whatever it happens to be. Okay, when that stuff strikes the earth, okay, or the precipitation lands on earth, it can be locked up. Right? If it falls as snow onto an ice cap or a glacier, it could be locked up into that glacier for a long, long time. Okay, there's some stuff that's in those glaciers that's thousands of years old. It's precipitation that fell on the top of a mountain 10,000 years ago. Okay, it's just been locked in that glacier for 10,000 years. Okay, it could also get locked underground. Okay, sometimes water will penetrate through the soil and into underground hollows, okay, called aquifers. If you have a well at home, you tap an aquifer to get that water for your well. Okay, the well is actually just the pipe that goes into the aquifer. Everyone follow me there? Okay, so if that's locked away, then it's kind of out of the water cycle for a while until it's either withdrawn or something like that. Okay, so it can get locked away. That process is called infiltration. Now you can't see it really well there, but okay, so infiltration is the process of water kind of percolating down through the soil and ending up in your well. Okay, it can also get trapped in lakes and ponds. Okay, if it runs off of a mountain but doesn't have access to a river or a stream, then it gets trapped in the lake and it stays there for a while. Okay, but most of the water that hits the ground runs off. Okay, it ends up in a river system and eventually makes its way back to the ocean. Okay, so that's what we call runoff. So this process here would be runoff. Okay, everybody with me on that? Will I possibly ask you to label a water cycle diagram and a multiple choice item? Probably. Make sure you know infiltration and runoff. Those might be new. Okay. Yeah, it just ends up back in rivers, takes it back to the ocean. Okay. If it's running off, it's going to eventually get to the ocean. Okay. Infiltration means it can get locked up. Okay, and it can get locked into ice sheets and stuff as well. All right. So the water cycle is always, though, conserving all of the water. Okay, there's the same amount of water on Earth now as there ever has been. Okay, it's always being recycled. The water in your water bottle today could have been dinosaur sweat. If dinosaurs sweat, I don't know. Okay, 65 million years ago. Okay, it could have been anything. Okay, it's just always evaporating and coming back. No, that's freshwater storage in the form of ice. Okay, infiltration is just the process of it getting through the soil and into an aquifer. Okay, an aquifer is also freshwater storage, but in a different form. Yeah. Kelvin? Oh, I didn't say that the distribution of the water was the same, but the amount is. How much ends up in the ocean and how much is fresh is always changing. Okay, their concern is that the amount that's in glaciers and lakes and rivers is decreasing. Okay, and that's true, but it's also been decreasing for 10,000 years, right? Like the last ice age was, the little ice age was a couple of thousand years ago. Well, that stuff's been changing pretty steadily for a long, long time. Right? But yeah, I mean, our concern is if there's less fresh water is a pretty important resource, right? And so we need to take care of it. Okay, so most of the Earth's water, 97% of it, is saline. Okay, that means it's salty. It's in the ocean. Okay, can't use it for drinking. Right? Only a small portion, less than 3%, is fresh water. Okay, and 3/4 of all of that 3% is frozen. Okay, it's present in ice caps, okay, glaciers, and things like that. So the amount of liquid fresh water on Earth is actually very small. Right? Yet it is arguably the most important non-solar energy resource on Earth. All life as we know it depends on water. Okay. Okay, so we got the saline water, we got fresh water, okay, we've got glaciers, okay, and obviously glaciers are shrinking all the time. That's a big concern. Okay, and then obviously we can have groundwater storage as well, which we can tap with wells. Okay, we were talking about that. So this would be a pipe that goes down to an aquifer. Okay, and we can reach that water there. Now, is it like an underground lake? Is an aquifer like an underground lake? Well, yeah, it's actually in kind of a rocky area. It would be more like if you put a bunch of like the rocks that you put in a fish tank. Okay, like if you filled a glass with those rocks and then poured water into the glass, the water would fill the spaces between the little rocks. That's more like what an aquifer is like. Okay, it's not a layer of water, although sometimes it can be a little bit that way, but mostly it's porous rock that contains water in the pores. Okay, and so we just draw the water out of that. Okay, and it's relatively clean. Okay, and then lastly is the lithosphere. Okay, the litho means stone. Okay, so the lithosphere is all the rocky parts of the earth. The most important part of the lithosphere is the soil because it's the topmost layer, it's the part that interacts with the solar energy the most, and it's where plants grow. Okay, without it, there'd be no use of the solar energy. Now, in terms of transferring energy from one place on Earth to another, the lithosphere basically has no role in that. Okay, it has an important role in the use of the energy coming in, sometimes the absorption of the energy, but not in the transfer of it because it's solid. Okay, it can't flow. All right, energy transfer occurs more effectively through fluids, the atmosphere mostly, and to some extent the oceans and the hydrosphere. But the lithosphere can't transfer energy very effectively from one place to another because it's a solid. Yes, yeah, it's moving air. All right, everybody okay with that idea there? Okay, so there's, when we're looking at the lithosphere, like we said, soil is the most important part. Is soil the same everywhere? No, it's very different everywhere you go. If you haven't noticed that, okay, look a little closer the next time. Okay, but soil is very different. Here around our area, the soil is quite sandy. Okay, the reason for that is our bedrock is made out of sandstone. Okay, all of the bedrock around here is sandstone. So, okay, the soil that comes from that is naturally going to be quite sandy. If you go to other places, like if you go into the mountains, the soil is quite a bit darker and loose. Okay, because it comes from limestone. So it tends to be darker and looser. It's more loamy than it is sandy. Okay, you go further north to like Red Deer and Edmonton, and again, the bedrock changes, so the soil looks different. If you go to PEI, how many people have ever been to PEI? What color is the dirt there? It's red. That's why they make those tourist shirts, the dirt shirts. Okay, they put them in the mud and they turn kind of a brownish red. Okay, because the soil there is red. The bedrock there is red, so the soil is red. Okay, it all depends on where you are. Soil all serves the same purpose. It's a medium in which plants can grow, but it is different depending on where you are. Okay, it is, however, always an ecosystem that has living and non-living parts, so biotic and abiotic components. Jake. The sand is the soil. This is soil right here. Yeah, it's rocks. It's top layer, that's what there is. Is there something growing in it? Yes. Okay, so anything that's the top layer is soil. Okay, now if you're looking at the top of a mountain where it's just rock, there's not really much soil per se, no topsoil anyway. It'd just be what we call the parent material, which is what we'll look at next. Okay, soil comes in layers. If you ever dug a hole as a kid, you noticed that. Okay, there's the dark stuff, and then it gets kind of clay-like, and then there's rock. Okay, at least around here, you don't have to dig very far before you hit the rock. I learned that when I was putting in my fence. Okay, I had a guy come in with a bobcat, and he was able to go down about this far, okay, before he hit the bedrock. When they dug the hole for my house, they pulled pieces of rocks of like sandstone out of there the size of a Volkswagen. Okay, they just had to break it up. Okay, there wasn't very much soil. Okay? So there's topsoil, which we call the A horizon. You need to know this. A horizon is topsoil. Okay, the B horizon is subsoil. Usually it's full of clay. Okay, and we'll talk about why that is. And then down below that is what we call the C horizon. Okay, and the C horizon is parent material. Okay? And the reason we call it parent material is it gives birth to soil. Okay, it's the erosion of those rocks, that parent material, that leads to the buildup of dirt. Yes, A, B, and C horizons. Okay. All right. Yeah, you wanted to know the O horizon, just A, B, and C. That's what we're most concerned with. So in this soil profile here, okay, you can see that this is the A horizon, kind of here. Okay. In this case, that's not a very thick soil. Right? But there's an A horizon there that would be full of topsoil that would have loam, organic material, some sand, a little bit of clay. Okay. Then underneath that is the B horizon. So this is A, okay, this is B here, and the B horizon is mostly clay. The reason clay ends up underneath, and it happened in your sandbox too if you were a kid and had a sandbox, okay, clay was always on the bottom. And it's not because your parents put clay on the bottom of the sandbox, okay, it's because clay is very fine. Okay? If you were comparing it, dry clay particles would feel like flour between your fingers, okay, or something like that, or cornstarch. It would be really smooth and very fine between your fingers. Whereas soil feels coarse, right? Because it's got sand and other things in it. So when you put it between your fingers, it's coarse. You can feel the little rocks, okay? But clay is very, very fine. So it washes down and through the A horizon because these particles are big and there's spaces between them that the clay particles can fit through when there's moisture. Okay, so the clay washes down and ends up underneath always. Okay, but it can't go any further than this because down here is the parent material, the rock, the bedrock, okay, the C horizon. Okay, questions on A, B, and C horizon? Okay, they're very different wherever you go. Okay, we're pretty lucky. On the prairies, we have a pretty thick topsoil most of the time. Okay, but if you go to like the tropical rainforest, oddly enough, it has basically no topsoil because it always gets washed away. And it's always when there's always flooding, so it always gets washed away. The clay solidifies almost and doesn't wash away. So the top of the topsoil in tropical rainforest is almost gone, and it's always B horizon that the plants grow right out of. All right, so the A horizon is the topsoil, and it's a mixture of decomposed rock, living organisms, okay, and decaying organic material. All right, so here's just another soil profile. You can see the A horizon is quite a bit bigger on this one, okay? The B horizon's about there, and then there's the C horizon down below. Okay, typical prairie soil, okay, has a lot of A horizon. The reason for that is every year grass dies and the next year it grows back. So there's always a layer of roots and leaves that are going to decompose and build up more soil. So we build up a very thick soil. Not usually. No. Like the bacteria and stuff that decompose them only live in this layer. They can't live further down because there's not enough oxygen. Right? There's a number of factors. If someone in agriculture overworks their soil, it has to do sometimes with the crops you grow. Um, like most farmers will rotate what they grow on the same piece of land, right? You don't want to grow canola every year because canola is a very nutrient intense plant and it basically strips the soil. So, the following year they'll usually plant something that rejuvenates it a little bit, like field peas or beans. They'll put a lot of nitrogen back in the soil. So they'll grow those and then maybe, some grain the year after that. But yeah, if you just grow canola every year, you've got to throw fertilizer on it like crazy. So yeah, typically they don't do that. The more you work the soil, like most of the time now, like most farmers don't till, right? They do what's called zero till, which is they'll cut the crop off from the year before, and then the next year when they seed, they just seed right on the stubble from the year before. Because the more you till it, the more moisture you lose. And if you lose moisture, if a wind comes up, it'll blow some of the soil away in what we call soil erosion, and you don't want that. It takes a long time to build up soil. So the more you work it, the more moisture you lose and the more soil you can lose. So most of the time, farmers try not to do that unless they're breaking something up that needs to be broken up. Okay, like we said, the B horizon has very little organic material. Rock is less decomposed, and there's a lot of clay. Okay, they can often be reddish in color as well. Okay, not always, but sometimes. Tropical rainforest, like we said, very thin A horizon, big B horizon, right? Because clay can typically cement itself together and not wash away in a flood. Okay, and then the C horizon would be underneath that. right? And then the sea horizon, like we said, is rock. Okay, this is a typical soil horizon from like in the foothills. Okay, topsoil is fairly thick. Okay, the B horizon starts to get chunks of rock in it, and then below that is kind of your bedrock, large chunks of partially decomposed rock. Yes, it's just they deposit based on their particle size, finest particles getting furthest down. All right, so solar energy budgets. What happens when the solar energy comes in and hits the Earth? Well, it can be absorbed, it can be reflected, or it can be used or converted. Okay, the Earth's a system, and the only input of energy we have of any like real influence is the sun. Okay, so we got to make sure that the amount of energy being used and being lost, okay, kind of all works out. Okay. Yeah, so this is kind of simplified. Obviously, energy strikes the Earth, and a lot of it gets reflected. Okay, some of it gets absorbed, not all of it. Okay, if we're looking at kind of percentages here, and you're never going to need to know the percentages, we start up here in space with 100% of the energy. Okay, going in a little bit. Okay, so by the time we get down to kind of this point here, about 16% of it has been absorbed. Okay, 6% of it has been backscattered. Okay, going just kind of penetrating into the atmosphere. Okay, a little bit further down, we start hitting the tops of clouds. What color are the tops of clouds? White, so they reflect. Okay, you're looking at about 20%. Okay, and then a little bit further down, about another 3% being absorbed by the clouds. Okay, and then the rest of that is getting to here, about 51% getting actually to the ground and being absorbed. Okay, whereas a lot of it will reflect off as well. Okay, and then the Earth obviously also emits a little bit of light to get a little bit of heat, okay, from certain processes, so that all kind of gets on its way out. Now, the more greenhouse effect we have, the more of that escaping radiation doesn't escape, gets reflected back down, okay, and it gets warmer. Okay, so like we said here, the main source of energy is the sun. Gravity, magnetism, and geologic forces are negligible by comparison. That doesn't mean they're not important and can do work, but by comparison to the amount of energy we receive from the sun every day, they're nothing. Okay. Okay. So there's 3 ways energy can be transferred. Okay. So if energy is going to move from one place to another, it will do that by one of 3 processes. Okay. Those processes are convection, conduction, and radiation. Okay, those are 3 we need to know. Have you guys heard those terms before? They used to be in Science 9. I guess they aren't anymore. Okay, so conduction is the transfer of energy in solid materials. Conduction is not a very effective way to move energy, right? Which is why we said the lithosphere doesn't have much of a role in terms of energy transfer. It does in terms of energy absorption, but not transfer. Okay? The reason being is in conduction, the only way that energy moves from one end of a solid to another is by particles running into one another. Okay, so if I heat up this end of this solid material, let's say it's metal, okay, the particles on this end that are over the flame start to do what? They start to move faster and faster. Okay, unless you're at absolute zero, particles are always moving. Okay, they're always moving around. Okay, but because they're in a solid, they're so tightly packed, they always are running into each other. Well, if they're moving around a lot, there's a lot of collisions that are going on. Okay, and eventually those collisions transfer along the solid material. How many people have ever been in a mosh pit before? Okay, really? Live a little. Mosh pits are fun. Oh no, it's lots of fun. Yeah, crowd surfing. Yeah, it's a great time. Okay. See, it's just showing how old I am. You guys don't do that anymore. You're missing out. Okay. Anyway, how many people have ever seen what a mosh pit looks like? Okay, that's a little bit better. Okay, so we've got people are tightly packed in there, right? But they're jumping up and down and bumping into one another. If you're in the middle, it's crazy. Okay, because people are always running into each other. Okay, especially near the stage, right? But the further back you go, okay, there's less of that movement. Okay, so there's less of that contact. People, aren't moving nearly as much. Okay, it's kind of like what's going on here. Here it's very close. Okay, the particles are moving a lot. Okay, but you can see that the particles are moving less as I get toward this end. But eventually, that heat will transfer. That motion that's here transfers out to here, but it's very, very slow because it depends on particles colliding. And the particles can't get past each other. Okay? Particles can really just oscillate kind of back and forth like this. Right? If they could get past each other, it wouldn't be a solid, it would be a liquid. Then it would flow, right? That's why a liquid can flow and why a gas can flow. The particles can switch places and go wherever they want. Okay? So conduction, not a great way to transfer energy. Okay? And it only works in solids. Okay? Convection is probably our most important method of transferring energy on Earth. Okay? Because it's what the atmosphere does. It's wind. Okay? Convection is like a current. Hot air rises, cool air descends. Okay? That's convection. Right? Your house uses that all the time. If you have a forced air furnace, it's using convection, right? It blows the hot air through the vents. And where are the vents located on the main floor? On the floor, right? Okay. You don't want to put them up top. You have to sometimes in the basement, but okay. On the main floor anyway, we put them on the floor because we want the hot air to come out of there because the cold air is on the floor. We want the hottest air to meet the coldest air and start a current forming, and that'll transfer the energy effectively through the house. Okay. Everybody kind of follow on that? All right, so we got our convection currents. Okay, that's going to transfer energy within both the atmosphere as well as the hydrosphere. Okay, but that is by far the most important energy transfer method. Okay, now radiation, I'm not saying radiation is not important, but radiation is. It's how the energy gets here. Okay, it travels as radiation from the sun to the earth. Right? Radiation is any energy transfer by waves. Right? You can't see these waves because they're light, but you can sometimes see their effect, and you can definitely feel when you're getting hit by heat waves. Right? If you ever had a campfire or you got a fireplace in the house or whatever, right? When you get close to it, you can feel the heat coming off of it, right? You even got like a little radiant heater, just a little electric heater. You get close and you can feel the heat coming off of it. That's radiation, not the kind that turns you into a superhero. Okay, that doesn't happen either, by the way. Okay, but the kind that's hot. Okay, that's infrared radiation or heat that's coming off of that heat source, and we can feel those waves. Sometimes on a hot day, you can see that kind of effect a little bit above the road, right? Kind of looks like the road's got water on it, but it doesn't. It's kind of wavy above. It's kind of a little bit of that. You're seeing the waves distort the air a little bit. Okay, it's mostly convection that's actually doing that, but the waves are also kind of playing a part in there. Okay, so radiation is any heat transfer by waves. Everybody with me on that? Okay. One of the things I'm going to ask you to do in this unit is apply what you know about convection, conduction, and radiation to a practical situation. As an example, okay, this insulated coffee mug is an example of harnessing these three methods of heat transfer, or rather not harnessing them, but preventing them. Okay, the inside of this cup, I can't show you because it's still full of coffee, but the inside of it is very light in color. Why? Right, light colors reflect light, and heat is a form of light. So if I have the inside of this being light in color, it's going to reflect the heat back, and so it doesn't escape. All right. If I don't want to have convection happen, how do I keep convection from happening? Convection is a current. How do I keep a current from forming? Okay, I can seal it, okay, and does a pretty good job of that. Okay, but if it's insulated, how does insulation prevent convection from happening? It doesn't absorb it, because if it absorbed it, that means that it's in the insulation and not where I want it. It prevents the movement, exactly. Okay. Now, for like a true thermos mug, it's actually a vacuum. There's two layers in here, and there's a space, a vacuum between them. If there's no matter in there, then there's nothing that can move. So you can't get a convection current happening between the inner layer and the outside layer. Okay. All thermoses work that way. Okay. But if you're with your house, it's not practical to make a vacuum between the inside walls and the outside walls because anything could penetrate it, right? Like first time you hang something on the wall and make a hole and it's done. Okay, so what do we have inside the walls? Sometimes it's styrofoam and sometimes it's fiberglass, right? Either one works the same way, okay? They prevent convection from happening. So if I have an uninsulated wall, okay, inside, outside, okay, this wall is hot, this wall is cold. Well, energy naturally flows from hot to cold. So, okay, you're going to get a current that's going like this. The heat's going to go towards the outer wall. That's going to get the air inside that wall moving, and you're going to get a convection current happening inside the wall that rapidly pulls heat out of the house. Okay, everyone follow me there? That's why your windows are one of the biggest places where you lose heat, okay, because they're not as well insulated as your walls. Okay, so that process happens very easily. Now, if I insulate that wall with fiberglass, okay, what I've done is filled up the wall with little glass fibers. Obviously way more than this. I just can't draw them as small as they are. Okay, so all these little glass fibers have air trapped between them. The key here is that it's trapped. What can it not do? It can't move. If it can't move, it can't send up a convection current. Okay? If a convection current can't get set up, I eliminate basically the biggest way that energy could leave my house. Okay, through convection. Now, through your windows, you lose energy through radiation as well as convection, which is why you want to have like drapes or something like that that can be closed on a cold day. Okay, or you want to have like the low E windows that have 2 panes of glass and a vacuum layer in between. Okay, they can be a little bit better at preventing heat transfer. Because a steel beam will conduct heat through. Okay, this is also going to prevent conduction because conduction can't occur through a gas, and there's a whole bunch of trapped air in here, right? And because these are all individual fibers, very few fibers are actually going to reach from one wall to the other, right? So heat's not going to conduct through it. Heat also doesn't conduct well through glass. Glass isn't just not a material that does that well. Okay, so fiberglass is a good material for that. Styrofoam works the same way, right? There's air pockets in the styrofoam that trap air so that it can't move from inside to outside. So that's why those materials work as insulators. Okay, everybody follow me there? How many people have ever built a quinzhee? Okay, you make a pile of snow and then you hollow it out. Okay, you can get it pretty warm in there, right? Okay, and you can get it warm in there because snow is white. So if you're inside, your heat reflects back at you. Okay, and what's trapped between all the snowflakes? Air. Snow is an excellent insulator. Okay, when we had all that snow sitting on top of our houses, we were getting extra insulation from that snow. Okay, first you got all the fiberglass you got in your roof, and then we had like another foot of snow on top. Okay, which is an excellent insulator, and it happened right before it got really cold. Okay, so we got actually a little bonus there when it was really cold with all that extra snow insulating our roofs. Okay, so when you build a quinzhee, you're doing exactly the same thing. The snow interlocks and creates trapped air that will insulate you against any heat loss. Okay. Yep. Yeah, you just keep heaping snow onto a pile. It's got to be like light, fluffy snow. It can't be packed snow. Like you couldn't use what's out there now. Okay. But yeah, and then you just hollow it out and you can sit inside and be warm. It's an emergency shelter kind of thing. Okay. What if I want to do the exact opposite? What if I want like to build a solar water heater? What would I make that look like? I'd probably want it black. Yeah, I'd probably want it black because black will absorb a lot of heat. Okay, and do I want the heat to get into the water quickly? Yeah, so I'm probably not going to insulate it, right? I'm going to want stuff that will not only convect, but also conduct heat from outside to inside. So it would be the exact opposite of what we're doing here. Okay, I'd want to harness and absorb as much energy as possible and transfer it as quickly as I could into it. So I'd use something that's a good conductor of heat, okay, in the pipes, okay, and something that absorbs a lot, but I'd probably paint them black, okay, something like that. Okay, making sense? Those are the kind of real world applications I would ask you to explain. Okay, so I'd give you a situation where here's a structure, or design a structure that could keep food cold, or or something like that. Okay. If we have time, but mostly it'll be. I mean, you guys can think that stuff up. I think you could. Okay. Like if I asked you, you're in California, and you need to build a building that'll keep frozen food in it. Okay. You can put one refrigeration unit on it. Where would you put it? Up. Yeah. Okay, put the refrigeration unit up here, because where does hot air go? Up, right? So this thing is capturing all the hot air, and because we learned how heat pumps work, and an air conditioner is a heat pump, this is the best place to vent it, right? If it's on top, I can vent that hot air up and out of there, okay? And I keep most of the food, hopefully, down near the bottom where the coldest air would be. And then I'd make the outside of it what color? White, or maybe even I'd bury it, right? Make it underground or something like that, okay? Would I insulate the walls? Okay, why would I insulate the walls? Well, because of this, right? That's the kind of thing I would ask you to do. Yeah, that sort of makes sense? Just applying what you know of conduction, convection, and radiation. Okay, within the hydrosphere, okay, the biggest energy transfer in the hydrosphere is this stuff. We talked about it a little bit before, latent heat, okay, that energy that gets absorbed, okay, when water changes state from liquid to gas. It also absorbs when it changes from solid to liquid. Yeah, okay, energy is absorbed in that process as well. Okay, so latent heat has to do with any change in state of water. Okay, it'll absorb that energy and hold on to it until it changes back into the other state. And when it does that, it releases that energy. And we're not talking about a small amount of energy here. Okay, for 1 gram, of water at 100 degrees, so already at 100 degrees Celsius, okay, it takes 2,260 joules of energy to turn it into a vapor. Okay, so you have an entire cloud full of water vapor move from one place to another. Is that a lot of energy? Yeah. Okay, so we're talking about a lot of energy moving in the form of latent heat from one place to another. Okay, that's why it takes so much energy to build a hurricane. That's why we don't get hurricanes here. Okay, there's not enough A, water, and B, energy to form a storm of that magnitude. Okay, they only form near the equator where there's enough water and energy to build a storm like that. Okay, making sense? Okay. So latent heat is the big thing for the hydrologic transfers, and we'll talk more about latent heat later on in the week here. Okay, ocean currents can also transfer energy. Okay, are we seeing a lot of the factors affecting climate starting to creep back into this? Okay, so that's something to think about too, right? Okay, and then lithosphere, like we said, there's not a lot of transfer that goes on in the lithosphere. The role of the lithosphere in terms of energy is provide a place for plants to grow and absorb energy. Okay, that's really about it. So if energy gets absorbed, the temperature goes up. Okay, but we're not talking about a transfer from, South America to North America through the Earth's crust. Okay, there's not heat transferring that way. Okay, that's got to transfer through the atmosphere because it's fluid. All right, so like we said, the formation of soil and growth of plants. Okay, plants take up those substances from the soil and store chemical energy in their tissues. So this is the lithosphere is more about the use part of the equation than it is about the transferring part. Perfect. We actually got through all of that. I'm going to end it there. Okay. Tomorrow we're going to talk about wind patterns and energy transfers. Okay, and then probably start on specific heat capacity tomorrow.